Dear colleagues, dear participants of the conference, today I would like to present our research entitled Entropy-guided feature engineering for intelligent decision support in municipal organic waste management. The motivation for this work comes from the fact that municipal organic waste management has become one of the most important environmental challenges for local communities. In practice, municipalities often operate under conditions where waste generation is influenced by many diverse factors: population density, seasonal instability, infrastructure limitations, environmental sensitivity, transport logistics, and social economic difference between settlements. Because of this complexity, traditional analytical approaches often do not provide enough support for decision-making. In many cases, local authorities need not only described statistics but predictive tools capable of identifying which territories may become environmentally weak in advance. That's why our study focuses on building digital analytical frameworks that combines environmental data, entropy-based features, ranking, and machine learning methods in order to support more informed municipal decisions. The main purpose of this research was to justify a data-driven approach and to build a digital frameworks for risk-informed municipal organic waste management based on multifactorial environmental data, information entropy, and predictive modeling methods. To meet this goal, two key research tasks were addressed. First, we developed a conceptual model of risk-oriented municipal organic waste management where environmental risk is considered as a result of a simultaneous influence of many heterogeneous variables. Second, we implemented a full digital workflow that allows identifying informative factors, building predictive models, and generating decision support outputs for local communities. In other words, the research combines methodology justification with computational implementation. The framework itself is organized as a sequence of interrelated analytical stages. At the foundation of the framework lies the initial analytical matrix, which you can see on the screen, where each row corresponds to one municipal observation and each column corresponds to one explanatory feature. In practical terms, this means that we integrated into one common analytical space social indicators, spatial parameters, waste generation variables, infrastructural indicators, environmental measurements, and temporal factors. The importance of the steps is that municipalities usually propose fragmented information, while the proposed framework transforms this heterogeneous data into a unified predictive structure. Another important advance is that the framework does not simply accumulate variables, but also reduces redundancy before predictive modeling begins. This slide presents the conceptual model of risk-based municipal organic waste management. As you can see, the model starts with raw multiple information collected from several groups of variables. This includes social demographic indicators, specific characteristics, infrastructure data production indicators, environmental parameters, and temporal descriptions. Before predictive modeling, all data pass through pre-processing stages: duplicate removal, consistently verification, treatment of missing values, and normalization. Then entropy-based evaluation is applied to determine which variables carry the highest information value. Finally, selected features are used for machine learning prediction and generation of management outputs. So the conceptual model ensures that each decision support output is analytically justified. We present the characteristics of variables included in the model. Each variable group performs a specific analytical role. For example, social demographic variables such as population and households reflect the scale of potential waste generation. Spatial variables include area coordinates and distance to water bodies, describe territorial environmental sensitivity. Infrastructure indicators characterize operational pressure on collection and treatment systems. Production variables represent real waste generation flows. Environmental indicators such as methane concentration and moisture reflects ecological conditions. And finally, temporal variables capture seasonality and cycle fluctuations in waste generation. Such grouping is important because it improves interpretability when discussing results with local decision makers. A central methodological component of the study is entropy-based feature relevance estimation. The entropy for each feature is calculated using the following extension. If feature values are distributed almost uniformly, entropy becomes high, meaning that these variables carries relatively little discriminant information. If the distribution is heterogeneous, entropy becomes lower, indicating strong explanatory importance. Because on entropy, divergence coefficient and future weights are calculated, after which variables are ranked according to the relevance. This allows us to reduce dimensionally while preserving predictive power. In practice, the steps is extremely important because this municipal datasets often contains many correlated variables. After feature ranking, predictive modeling is performed in Google Colab. The full computational workflow includes data input, train test splitting, model fitting, validation, prediction, and benchmarking. The computation implementation was developed in Python using NumPy, Pandas, scikit-learn, matplotlib, XGBoost. This environment allowed us to test several machine learning architecture and indicator. An important methodological point is that five-fold cross-validation was used to improve robustness of the result. The general forecasting model is represented, as you can see in the slide, where the trained machine learning model maps selected feature in the predicted environment risk index. Four algorithms were compared: ridge regression, random forest, gradient boosting, XGBoost. The comparison was performed using the three standard metrics: MAE, RMC, R. This allowed us to objectively determine which architecture provides the best forecasting quality. The comparison clearly showed that entropy-guided feature selection improved predictive performance. The strongest result was achieved by XGBoost. This indicates that assembly boosting methods are especially effective when environment risk depends on nonlinear interactions between variables. An important observation is that entropy-based feature ranking improved interpretability without sacrificing predictive quality. Based on predictive results, specialized visualization was performed for settlements of the Sheptytska community in Lviv region. The predicted environmental risk index was interpreted according to the three levels: low risk, medium risk, high risk. This map demonstrates that the risk distribution is not uniform across settlements. Some locations demonstrate significantly higher predicted environmental pressure. Such special outputs are especially useful because they immediately support municipal prioritization of environmental intervention. To summarize the main results, first, a few digital frameworks for risk-informed municipal organic waste management was developed. Second, entropy ranking allowed independency of the most informative variables, among which tourism intensity, income level, area urbanization level, and distance to water bodies were dominant. Third, predictive modeling demonstrated high forecasting quality, particularly with XGBoost. And finally, special interpretation showed local areas where environmental management measures should be prioritized because predicted risk value ranged from 0.5 to 0.7. This means that proposed framework can serve not only as a research model but also as a practical analytical instrument for municipal ecological planning. Thank you very much for your attention. I will be glad to answer your questions.